Welcome to Thermal Engineering Concept and Principle. This is Professor Ali Tarra. What do you know about vertical heat exchangers and their philosophy of operation with geothermal heat pumps? We mean here the operation of the borehole geothermal heat exchanger. To know that, come with me to go through details of the present episode. Welcome, my friends and colleagues, to introduce the aspect of thermal design for the boreholes in a geothermal heat pump. In this episode, I will introduce the characteristic of a borehole heat exchanger and its installation in the ground, accompanied by its main components to construct a heat exchanger that is called borehole type, which is a vertical heat exchanger. In this part, I will cover the construction of the heat pump itself and the borehole and how can we estimate the depth of the U-tube in the ground, which is related to the properties of the geological aspect for the ground and the thermal properties of the grout or filling that is surrounding the U-tube in the ground. Thank you for continuous support and let us keep on this series of videos in this field, which is the renewable energy source called geothermal energy. The objectives of the present episode cover the geothermal heat pump components. The main components, of course, I will pass through. And then we have the direct contact geothermal heat pump, which refers to the contact between the heat exchanger, which handles the circulated fluid in the heat pump, and the ground. Then we will go through the estimation of the depth for this heat exchanger, which is in effect, we are calculating the surface area of the heat exchanger to achieve a certain heat or cool load. And finally, we will approach, as usual, the closure for the present episode. In this system, we have the heating mode, where Earth works as an energy source to the fluid which passes through the borehole in the blue direction, which extracts energy from the ground and then return back to a heat exchanger
which is a part of the heating pump, then this fluid will give energy to another circulated fluid, which we have explained in the previous slide, and then that will provide energy to space. In that way, we have extracted energy from Earth and transferred to the, for example, domestic use in this example, then heat can be transferred from ground to the utility. In this case, we have the utility as heating for um, house or maybe in a restaurant or other applications. So this is the heating mode, how the heating mode operates. Here we have a vertical heat exchanger, which is called borehole heat exchanger, that is installed vertically inside Earth. It is composed of uh, U-tube, and the U-tube is installed inside a bore surrounded by grout material, and this grout material should be conductive material to facilitate heat transfer and conduction between the soil, the external part as shown in this figure, and the tube itself. So in that sense, we are uh, extracting energy from the soil, which represents the earth structure, conducted to the grout, through the grout material, to the tube surface, all of that in conduction, and then by convection to the fluid which is passed inside that U-tube, and it could be water, shown in the right hand side photo, water inlet and water outlet. Water inlet representing the blue one, and the outlet is the green one. So hot fluid or hot water, we will get it from that bore hole, and can be used for heating purposes. Almost similar system can be used for cooling system as well.
Here we have the condenser, which represents the fourth main part of the heat pump itself. So we have the underground heat exchanger, the borehole, represents the condenser, and the other parts which compose of evaporator, compressor, and expansion valve, represented by the other side, which is out of the ground. Then what we have, the ground part represents a condenser. Here we have the refrigerant vapor, which is circulated in the heat pump, passes through the inlet part of the heat exchanger through the red line, and then it reject energy to the ground, of course, through the filling or the grout to the ground, and then returns as a liquid refrigerant to complete the closed circuit of the heat pump. Again, this is a DX geothermal condenser because we didn't need an intermediate fluid to transfer energy to the ground, because the main principal part, which represents the fluid that is circulated in the heat pump, is the liquid which passes through the heat exchanger. Borehole depth estimation and the length of the heat exchanger. In the present episode, we will illustrate new correlation and model for prediction of the heat exchanger length. Let us assume that we have a single U-tube in a well surrounded by grout, and to present a geothermal heat exchanger. We want to get a general form to predict its length. We will transfer this U-tube to a single equivalent tube with a diameter d sub e. The first assumption depends on considering that the volume of the grout material is fixed for both geometries, which leads a final form for the equivalent diameter to have the value square root of d naught, as shown in equation number 1. The second step in this model, I will transfer this equivalent diameter to a position in the borehole where we are keeping the offset distance and the shoulder between the external surface of this tube and the borehole diameter fixed. That is corresponding to a value equal to U naught, Y naught. And Y naught, as presented in equation 2, if we used it to present the value of L sub PE, which represents the distance between the center of the equivalent tube and the center of the borehole, can be obtained in the form L sub PE equal to half times d sub b minus 2 u naught minus the equivalent, which is represented by equation number 3. And we will use the same equation which we have presented in other or previous correlations and episodes, that the thermal resistance of the grout material can be represented by the offset resistance for a tube or cylinder inside an external cylinder for the shape which is representing the equivalent diameter. You may find all the details about this correlation in the reference shown at the bottom of this slide, and usually it will be the first reference in the list, which I am going to include in the description box of the present episode on the YouTube channel. To estimate the total thermal resistance of the borehole, let us consider this single tube arrangement where we have refrigerant vapor enters the heat exchanger at one leg and leaves as a condensate on the through the second leg, and then it will be called the DX geothermal condenser in a heat pump, as there is no intermediate fluid to be circulated between the heat exchanger and the rest components of the heat pump, because only freon will be circulated between the heat pump and this heat exchanger in the ground. And R sub B equal to summation of R sub F plus R sub P, and we have defined R sub P as the total specific thermal resistance of the pipe which composed of two components, the convection part and the second part is represented by the conduction part as shown in equation number 7. And to get the total thermal resistance as a specific value, we have R sub B plus R ground. And R ground is usually a dependent variable on the time, because the conditions are varied in the soil with the time, but equation 8 can be represented with a constant value of R ground because it has been found that after 1 year of operation for the heat exchanger, the geothermal heat exchanger, then the soil will heat transfer performance will reach steady state conditions with R ground equal 0.053 meter Kelvin per watt when the thermal conductivity of the soil was 2.42 watt per meter Kelvin. Then the heat loading equal to Q equal delta T mean divided by R total in watt per meter. And then we may find the depth of the heat exchanger by dividing Q dot condenser divided by the heat loading as shown in equation number 10 in the units meter. And the Q condensation will be calculated from the condensation of Freon R410A by multiplying the mass flow rate by the latent heat, and that will be represented in equation number 11. From these equations, we may estimate the Q value, in fact, which represents the heat loading of the heat exchanger. To investigate the present correlation, let us consider an example where we have a heat pump is used to cool down a space by using a geothermal heat exchanger as a condenser. And it has the cooling load of 3.5 kilowatt, where it can be used to produce cold water as 7 degrees Celsius, and then it can be passed through a fine coil where a maximum temperature difference can be obtained for the water to be 5 degrees centigrade. The evaporation and condensation temperatures are shown in this expression that for evaporation temperature is minus 10 degrees Celsius and a pressure of 5.72, and then the condensing temperature and the pressure were 30 degrees centigrade and 18.76 bar respectively. Of course, these values representing the operating conditions for the refrigerant, which is R410A, circulated in this heat pump. The rejected load was estimated to be around 4.4 kilowatt with a COP of this heat pump to be 3.57 for cooling. And the condensation heat transfer has been used as a typical value for this refrigerant to be 3000 watt per meter degree centigrade. The upper or the tube itself is composed of a single tube made of copper, and the table shows two different geometries to be examined in the present episode. Of course, we have to use a thermal conductivity for the grout material, which we have selected even in previous episodes when we have examined the other correlations to be in the range between 0.73 to 1.9 watt per meter Kelvin. Results comparison between the present episode correlation and the others, which have been expressed in different and published in different journals for me and for others, can be presented in this part. We have the equivalent, which has been expressed as the square root of d naught, and it has been calculated and included in this table. The variation of the group specific thermal resistance and its variation with the thermal conductivity can be shown in this figure for the geometry G1. And it's clear that all the behavior of all of these correlations have the same trend. We have the maximum value is around 0.35, where the thermal conductivity of a groot was 0.73, and it has been predicted by Tarad star, and this is a previous correlation, and the minimum was predicted by Raymond. It was around 0.25 meter Kelvin per watt, and the minimum value was obtained when the thermal conductivity is around 1.9, which is the highest thermal conductivity in our examination, and it was around a value which is less than 0.15 for Tarad star, and it was less than that, around 0.1 for Raymond. This is for geometry G1. And for geometry G2, we have the higher value was predicted by both Etal and the minimum value by Raymond. It seems that Raymond correlation usually has the lower value among others for the thermal resistance, and all other correlations have predicted values in between and occupying the zone between the maximum and minimum values. The total resistance has been calculated for both geometries, and of course these values should be used to predict the depth and the length of the heat exchanger, which can be used to achieve a certain cooling load, which represents the condensation load for the refrigerant Freon 410A, which can be mainly depends on the total heat transfer rate and the temperature difference between the fluid and the soil which surrounds the borehole. To estimate the borehole depth of the heat exchanger, geothermal heat exchanger, which can be deduced, of course, from the length of the heat exchanger. It depends on the D equivalent, which has been calculated for both the geometries, and these values were used to estimate the groove thermal resistance and the total thermal resistance. These values were used to estimate the depth or the length of the heat exchanger for different values of temperature difference between the condensate and the soil. For this part, we have used a temperature difference of 20 degrees Celsius for geometry G2, and we have also examined the heat exchanger length where a temperature difference was 15 degrees Celsius. Of course, that increasing the temperature difference between the condensate and the soil will produce lower depth and lower heat exchanger length. And in this example, we have found that the highest length for a specific value of temperature difference was obtained by uh, both etal and the lowest was predicted by Raymond. Of course, these values mainly depend on the temperature difference and the total resistance, which has been calculated throughout this episode. And in that effect, we have to mention that the orientation of the single tube in the heat exchanger has no effect, in fact, because we are only dealing with one single U-tube, and this can be vertical or horizontal. So, in general, the length of the heat exchanger is higher for the lower temperature difference of between the soil and the condensate. Of course, more details can be obtained from our reference of the present correlation as shown in the list of references uh, uh, seated in the description box of the present episode. My friends and colleagues, we have arrived to the final part of this video, which is related to the closure. We passed through the geothermal heat pump components, the underground part, which represents the borehole, and the other parts which are on-ground parts, which includes compressor, expansion valve, and either the evaporator or the condenser for the direct geothermal borehole, where we have the fluid passes through the tube, the U-tube, and is the same fluid which is circulated in the heat pump itself. That's what we call the direct contact geothermal heat pump. And I used one of my published correlations to predict the depth of the single U-tube, and it was compared with other published correlations for specific conditions of the heat load and the physical dimensions of the borehole. There are some valuable references you may find in the link in the description box for some references which are either used in this episode or in you may increase your knowledge about geothermal energy with the others. And usually I put the reference which has been discussed in this episode as the first reference in the list. If you feel that the information and the thermal design is useful to you and others, please subscribe to the channel and share it with your friends. And we hope can achieve the main goals of our for the creation of our channel. Bye bye.